So this is a collaboration work with Phil Porras and Vino Ram from SR International and Professor Zhichang Lin from Ohio State University. So the short message service, or SMS, is a legacy communication protocol in the cellular network that has been introduced since a few decades ago. And the SMS is still widely in use in today's mobile systems. So SMS has a wide range of applications, including text-based messaging, two-factor authentications, alerts and notifications, marketing, advertising, and so on. So this diagram shows the typical SMS transmission paths in cellular networks. So here, the cellular mobile devices, such as the smartphones, are broadly classified as the user equipments, or UEs. So to initiate a SMS message, actually a UE first needs to transmit a SMS submit message to the nearby base station within the radio access network. So the network then forwards this message to a SMS center within the mobile core network, which further relays the message to another base station, which is close to the victim, the receiver device. So finally, the receiver will get a SMS deliver message, and this is a typical scenario of SMS-based SMS transmission, which is quite prevalent in the legacy 2G and 3G protocols. So in the more latest, like 4G LTE and beyond standards, it's more common for SMS messages to be relayed by a IMS server on top of the IP network instead of the mobile network. But this is all done in a similar architecture. So people may take it for granted that SMS is just a text-based service, but we argue that this is not entirely correct. In fact, there is a lot of zero-click exploits that exist in a variety of different ways that can compromise the security, the privacy, and even availability without the user's knowledge and consent. So this diagram shows a typical example of SMS exploit called Simjacker. This attack was discovered late until 2019, where an attacker is able to simply send out an SMS message with malicious binary attachments. That attachment may involve the binary code that will be executed on the victim's device. For instance, to execute commands to obtain the user's location and then send that location back to the attacker's device via SMS. Unfortunately, the contemporary UE operating systems cannot see these SMS attacks, let alone stop them. So here we would like to share more details about how an SMS can be exploited. So in fact, the structure of an SMS message is actually more complicated than we have imagined. And you can see here there's a lot of fields within an SMS payload in PDO mode, such as the protocol identifier, PID, and the data coding scheme, DCS. So one such variant of SMS that can be exploited is called silent SMS. So silent SMS is also known as the type 0 SMS. So as you can tell from based on its name, when the UE receives a silent SMS, the content of SMS will not be displayed to the user, which means there's no way for the user to get notification about the SMS or know the content just looking at the SMS applications. But still, the receiver will respond to the sender with an acknowledgement report. So for this reason, silent SMS has been, can be used by adversaries or other authorities to perform tracking attacks to track cell phone users' location. And it can simply use to perform denial-of-service attacks that can be conducted even without the user's awareness. So flash SMS refers to the class, which also known as the class 0 SMS, is the message that upon receiving the message, the UE will display a pop-up window, just like the one that we show on the right, with the content embedded in the SMS payload. So flash SMS can also be exploited for adversaries to, for instance, sending spoofed alerts to the users, or simply an adversary can flood the UE with flash SMS windows to essentially DOS the phone. So binary SMS, such as the Simjacker attack or WIBAttack that we briefly described before, refers to the SMS that contains malicious binary payload and commands that can be executed on the victim device. So this this process is actually transparent to the users, and the user definitely has no consent or knowledge about this. And there is a lot that can be triggered by a binary SMS attack, such as executing voice calls, SMS messages, or forcing the phone to open a browser, or even leaking the user's location or other identities. So the binary SMS is actually happened without any indication on the phone that tells you that command has just been executed. So another common threat of SMS is from the fake base stations, where the adversaries actually use many commercial software-defined radio devices to set up base station that can use high signal power to attract nearby devices for connection. So after that, the fake base station can send out spoofing SMS with the spoofed address to conduct attacks such as phishing attacks on the nearby devices. And this actually is quite prevalent in the legacy GSM network. And in some countries, it even allows the criminals to make huge profits by setting up fake base stations and send out such SMS messages. So malware SMS refers to the threat where the SMS is generated from malware-infected phones. So today there is many malware that can be distributed from some like app stores or through social engineering or malicious links. So this malware is good at impersonating themselves as legitimate apps, such as those with COVID notifications and postal services. So these malware apps will basically ask the user for the SMS permissions, and when the permission is granted to the malware, and it will automatically browse like the victim's contact list and send out quickly spread those malicious link or malware links to other users. So lastly, one of the very interesting SMS attack is actually called the proactive SIM SMS. So this stands for the scenario where some mobile operators or the supply chain attackers can actually insert proactive malicious logic within the SIM card that is distributed to the users. So this proactive logic will be activated when the user use this SIM. That will automatically generate SMS messages that may contain the sensitive information from the user back to another locations. So people may be curious, what is the exploitation cost of launching these SMS attacks? So the short answer is as low as only $20 if we just ignore the cost of using a desktop or laptop machine. This only involves like a prepaid SIM card and a GSM compatible USB modem in order to craft like a binary SMS message. So how should we defend against SMS attacks? So this is the typical architecture of a user device, such as an Android smartphone. And one way to do this is to deploy defenses at the baseband layer, such as, to our knowledge, some Qualcomm chips, they have deployed fake base station-related detection mechanisms in their firmware code. So the advantage of such defense is it has high visibility because the baseband basically has access to each cellular traffic and messages. And meanwhile, the baseband has the capability to block these attacks before the attack affects the user's security and privacy. So the limitations is that the baseband components are typically not open source and is often protected by signature verification mechanisms that stops unauthorized third parties to modify the baseband code. And the baseband is also highly customized, and it has different implementations from the different vendors. So another approach is to deploy defenses directly at the app layer. And we notice there are already Android apps to detect certain types of SMS messages, and there are other apps that can monitor the low-level baseband information. So the advantage of this kind of defense is the low deployment cost because it only requires the user to install simply an Android application. However, this kind of defense has low visibility and it only offers passive detection. It cannot block the attacks from that is already occurred, and it often requires the root permission. So to balance the trade-off between the advantages between the app layer defenses and the baseband layer defenses, we propose the first defense mechanism called RILDEFENDER. So our key insights is to deploy RILDEFENDER at the radio interface layer, or RIL. The RIL is actually a layer that generally exists in all Android UEs. And it is able to intercept all the traffic between the baseband processor and the Android processor. So WIBAttack emphasizes three key distinctions over the existing defenses, such as WIBAttack provides both detection and prevention capability to not only detect and block most of the attacks automatically. And WIBAttack is also vendor agnostic through different types of vendor-implemented Android rooms. And we also added extensibility to WIBAttack that allows users to dynamically integrate new signatures and policies. So this picture briefly shows the high-level architecture of WIBAttack, which is broken down into the IL part and the application part. So from the IL, we designed 4 logical components of WIBAttack, including a baseband monitor that monitors those SMS attacks that is baseband only. And we later show there is one exception that requires these components in our evaluation. So the baseband monitor basically intercepts the baseband traffic from the diagnostic interfaces in the Android devices, and it adapted from the existing baseband parsing libraries. So the context extractor basically tracks the context from the user space applications, such as the sender process ID of an SMS message in order to track whether this is generated from a legitimate source. And we also track the context of some system-level parameters, such as the average signal strength, in order to detect fake base station-related SMS attacks. And basically, these components interact through some IPC calls. So the attack detector basically instruments the main IL handler, and it synthesizes the SMS payload information and also other information from the components to make the attack detection decisions here. And it loads the user-defined attack signature sets. So the inline mediator basically instruments the IL logic for the attack prevention and interact through some specific IL commands. So at the application layer, we designed a WIBAttack app that is responsible for various tasks. For instance, the WIBAttack, the user can use it to configure the security levels of each of the attacks. And we also, it also receives the real-time alerts that will display it to the attacks, to the users for specific attack events. And it also configures the user-defined signature set for the SMS exploits. So we just briefly show the snapshots of the WIBAttack app UI, including the configuration UI and the alert UI here. And WIBAttack, by default, collect a set of features from the SMS payload and some of the system context information, such as the SMS fields from the payload and the SMS contents and the events. And these features can be used by a YAML-based language to describe the SMS attacks as the propositional logic configured through the WIBAttack app. So to evaluate WIBAttack, we have implemented a prototype based on the Android open source project, or AOSP. And we have targeted 5 different Android versions, ranging from the legacy Android 7 until it also supports the latest Android 13 version here. And this is the evaluation testbed. Actually, we use a Blade RF software-defined radio with the 8BDS radio switch to establish a SMS testbed to replicate the SMS attacks that we just now mentioned. And this table shows the SMS attacks, and including the variants that we simulate using our testbed. And here are the detection results shown in the last 2 columns. So as shown here, WIBAttack successfully detected all of these attacks and is able to block most of them except 2 exceptions, which are 2 binary SMS variants that is only processed within the baseband without passing through the IL. We further evaluate WIBAttack with malicious malware examples that will automatically generate SMS messages, including some open source remote access Trojan and real-world malware samples. And we found that WIBAttack successfully not only detect, but also automatically block them. So there's another interesting experiment where we test WIBAttack in a 7-day test campaign to test if WIBAttack can detect real-world SMS potential exploits. So surprisingly, we actually noticed there's a lot SMS happening here, including RILDEFENDER captures those silent SMS, binary SMS, and those SMS generated from some proactive SIMs, which are drawn here with the red markers. So we suspect these SMS messages are possibly generated from some mobile operators to communicate back to their servers. So we also evaluate RILDEFENDER's overhead, including its power, the memory, the storage, and the computation. So due to the time limit, please read our paper for the full details. So the future work. So first of all, we present RILDEFENDER as a defense mechanism. So it does not attempt to distinguish SMS attacks from those benign use cases. For instance, some law enforcement agencies, they use silent SMS to track criminals. While this can be easily addressed by some mechanisms such as SMS whitelisting, we put this into our future work. The other second future work is the automatic prevention of baseband-only SMS attacks, such as those two variants that RILDEFENDER cannot automatically block them. And the third one is the extension to IP-based SMS protocols and other like MMS protocols that, due to the AOSP restriction, we cannot implement RILDEFENDER to support these SMS scenarios. And lastly, the RL also includes many vendor-specific implementations like the RL libraries and functions. And the last future work would be to explore this kind of different functions to enhance RILDEFENDER. Similar like abstraction layer that handles SMS or other cellular messages. So I think that's a very interesting idea that we can extend our framework to. That's just a criteria to detect like fake base station related attacks that we consider as any fake base station. So one of the obvious distinction is this base station needs to transmit high signal power in order to track those smartphones. So there's already related papers that talk about how can use this signal strength to detect those. So that's why we introduced that component.